Huh?
I know it looks to be side.
Yeah, I know. Yeah, exactly. I had a problem with this question in the original notes because they talked about the original problem being in Benares. They talked about Buddhist monks instead of Hindu monks. Those are very upsetting to me. You saw that? Yeah, I was like, what? Anyway, I complained to Jeff about this. So this is so there's a question here. The goal is to find a recurrence to figure out how many steps it's going to take to solve this. The trick being that once you put things on the middle tower, you can move them all over in one shot, right? So one common mistake is to say, well, actually not a common mistake. Here's a solution that someone came up with, which in one way is very clever, but another way kind of defeats the purpose of this class. So the solution was, step 1, write code. That's fine, write some code. And code that you can actually run. So run the code, right? Compute, so output number of steps for n equal to 1, 2, 3, whatever. Okay? Then 3, go to the online encyclopedia of integer sequences. So in other words, Google. And find the name of the sequence. Okay? Now, if you're out there in the wild doing algorithms, this is a great way to solve a problem. There's absolutely nothing wrong with it. Because hey, you just want to know what the hell is going on. And you get the answer. It's great. I've done this myself, by the way. It's like this, I don't know what this is doing. Let me go find this sequence. Oh, it's great. So, if you did this, it's a good way to get the answer. But again, this class is not just about getting the answer. It's about learning the process for getting to answers. In that sense, this is a total failure. You have not learned a reliable, consistent process for getting to the answer. You found something that works in this case. Good for you. But if this step doesn't work, you are in trouble. Then we have to do this. I don't know if anyone watches South Park anymore. So if you had done something like this, or if you had written code and say, well, here's the answer based on my code, and I've seen this happen time and again in this class, in previous years as well. You'll write some sequence, okay, this is what it looks like. This is what it looks like is very good intuition. This is what it looks like is not a proof. Intuition is great. That gets you the guide to where you need to go. But it's not a confirmed answer. Okay. In this case, you actually have to set the recurrence. And in fact, there are 2 recurrences here. You need one recurrence to say how much effort does it take to move from straight to leaning. You need a different recurrence to say how much effort does it take to move from leaning to straight. You need to put those 2 recurrences together and then solve an overall recurrence. And then you get your, the Leonardo, derivative, Fibonacci, whatever you want to call it numbers. And if you actually set out to say, okay, let me write down the recurrence as we've been told in class, let me mechanically try to sort of do the algebra, you will get to the answer. And that brings up another point I want to make, right? That you need to, at some level, trust the process, right? So people come to office hours and they'll ask questions like, okay, I have this problem in homework 2, and here's what I tried to do. Right? So for example. And that's good. You're trying ideas, you're trying out things. But one of the things that I'm trying to push in this class, right, or at least in this initial section of the class, is that while algorithm design is not a science, there's enough science to it that you can apply standard procedures. And they might actually get you to a solution. So for example, if you're doing a dynamic program, there is something that you should be doing first. The first thing you should be doing is come up with a recursive formulation. If that's not the first thing you're doing, you're wasting your time. Because then what you're doing is trying to reinvent 40 years of what we learned about dynamic programming by yourself. Why would you want to do that? You should benefit from the knowledge that we've learned over the years. When the teacher in class is saying, just think recursively, implement bottom up, just do that. Don't try to come up with a first principle solution to the problem. Because that's a natural instinct. You see some problem, okay, let me just try to play with it and come up with an answer. We're at a level now in algorithm design where you should try to do that, because the problems you're going to face are harder. And if you try to go from first principles, you have to go back 40 years and learn your way back up. You don't want to do that at all. you want to use the templates that I'm trying to sort of argue that you should use. So if it's a greedy algorithm, you know, okay, I have a strategy, it's a local strategy, and I have to prove correctness. If it's a dynamic program, I have to do this recursive formulation, show by induction that's correct, and then analyze the runtime once I implement a bottom up. There's a formula for this. It's not a formula like, you know, x squared plus y squared equals z squared type formula, but it's still a template. You should use the template. Don't try to do it from scratch. Okay? Because if you use a template, it will tell you, okay, the template has these 3 little pieces. I need to focus on each one of these pieces. I need to focus on the recursive piece, I need to focus on the runtime piece, and I can do these things. You will find it to be a little bit easier to solve the problems if you do that. You will also find it easier to argue that your solutions are correct. Which brings me to my next point, right? And what I'm hearing is that, what I'm seeing from the solutions when we go and look at them is that a lot of times people will, how should I say this, a certain style of algorithm writing that I can only sort of politely term as throwing mud at the wall and hoping something sticks. So basically you write this 5-page extravaganza, hoping that somewhere in there is an idea that will actually be correct. Right? And then when we grade it, we read through that 5-page, you know, opus that you've written and try very hard to find the idea in there that's correct. But soon enough realize that this is not even, you know, I don't know if you've heard this phrase, it's not even true. Or it's not even false. You know, at least an algorithm that's well specified is either true, is either works or it doesn't work. Most of these things are neither. They're in some kind of quantum limbo of truth, which is very hard to discern what's going on. It might be correct, I don't know. The onus of proof is not on us to figure out where your thing might be correct. The onus of the burden of proof is on you to demonstrate that your thing is correct. So if you're writing out this opus, what's really happening is you have some idea in your head, and you've written it out and you don't know how to convert that into something more precise. So stop. Look at what you've written. There is probably a good idea in there somewhere. Do the work to pull it out. When you give your algorithm, justify it. Give an explanation for why it's doing what it's doing. You will find it'll be a lot easier for us to figure out what's going on. It'll be a lot more likely that we'll give you the correct marks for your answer and we won't have this long back and forth afterwards arguing about whether you have the right answer or not. And you will also be more clear in your head about whether your thing is correct. So, make sure to explain and justify. Writing code is not a justification. And I've said this before, and I've still seen solutions where people write code, even pseudocode, even code that you could run, and stop. Say, okay, that's my answer. No, that's not your answer. You have to defend it. In this class again, well, rigor, correctness, reasoning, proper reasoning. That's the point of doing this. That's why we have these toy problems. Right? Toy problems you may never encounter in this. But they're toy problems because they help you exercise your brain on how to reason rigorously. You have to do that here. It's not enough to give the answer. I want to see the process, the thinking. Okay? Finally, even though sometimes it's very artificial, it's helpful to separate out the algorithm, the proof of correctness, and the proof of running time. Sometimes it's weird because you have to keep repeating yourself because the algorithm has baked in something else. But it's helpful to write it that way because it forces you to think through explicitly, okay, what is making this algorithm work correctly? Okay, what's the runtime control going on here? And it's also easier for us to see where your contributions are. You may not know this, but we'll give you points if you have an algorithm that seems right, even if you haven't reasoned about it correctly. If you separate out, here's my algorithm, here's my proof of correctness, and here's my proof of runtime. If you get one of those last two wrong, you're not going to get 0. You're going to get points for what you did, and because if we can see, oh look, I think you got it right, but your reasoning was wrong, you'll still get marks on that. And if you separate these things out, we can do that. If it's all one big mishmash, it's very hard to tease these things out. Yes?
I think what maybe some of the confusion in the assignment is that you didn't say any of this in the assignment. You just said describe an algorithm, for instance.
Yes, and actually I did. I did one of my lectures before the assignment was due, I mentioned some of these things. I said specifically I want to see, for every algorithm, I want to see the algorithm, I want to see a proof of correctness, I want to see a proof of running time. I actually did say that because I know people do that. But I, even though I said it, I knew that it was only going to partially get home. So I did cover this in one of the classes before.
Right, it wasn't really emphasized. And like I said, in these problems, they just say describe an algorithm. You know what I'm saying? So when I'm reading the assignment, because I noticed on my grading that that I've been hit for that a couple times, like, hey, there's no proof of correctness or anything. But it seems like citing didn't count. Like if I cited the reading or cited
if you cite no. That's not correct, and that's, okay, so that's the other thing, redress. But if you have cited, if you've relied on something from the notes that would automatically prove correctness, then you will get points. If you cite some discussion in the notes that could potentially be used to prove correctness, then you won't get points. There's a difference. And having said that though, if you feel that you've got the answer correct, and there has been a mistake, which happens, we all make mistakes, put a comment in the sort of in the submission comment field. That's the easiest way to track what's going on, and that's where the discussion will happen, and we will go. But please do it soon, right? I know you're busy with the assignment now, but at least starting next week, start working on this thing. I don't want to have this prolonged over weeks and weeks. But this often happens. We'll make sort of errors in calculations here and there. We'll make errors in grading, and we will fix that. But put that in the comment feed. Don't email anyone individually. It's very hard to keep track of where the errors are. Okay. So that's one. So if you do feel that in fact you cited something that will correctly give your answer, then put that in the comment and we'll look at it.
So mostly as going forward, basically you're saying that when we go forward, if you say describe an algorithm, you actually mean describe the algorithm, prove its correctness.
So I'll repeat this again, but I've said this from day one of this class. This class is about rigorous, reasoned things. This is not about what I would call heuristics. This is not about things that seem to work because I ran some code and it looked right. This is about things for which I can prove correctness. Hopefully in the lectures I have been sending this message out by proving correctness for everything. That is always going to be the case. There is no, in this particular class at least, there is no room for informal arguments. The goal is to learn how to make formal arguments for things. That is always going to be there. For running time, for correctness.
So is there a body of knowledge that can be just assumed in here? I mean,
you can assume
how far
anything.
back do we have to prove things, I guess?
That's a good point. We need to prove that 1 + 1 is equal to 2, for example. And if you're a computer-generated proof system, sometimes you have to go back to that thing. You can assume true anything that's stated explicitly in the notes. You can assume true anything that I state in class. If I say Maxwell-Milken theorem in class, you don't have to prove it. I've stated in class, it's done. So and that again is what I mentioned before, the Aiken has given knowledge that can be cited and used without proof. Anything else? Maybe. Yeah. So you don't need a proof from Moss theorem. You can invoke the Moss theorem. Because we talked about this. Right?
So for homework too, if he can, for greedy algorithm, if he can give a concrete example of where a greedy policy would fail, for that one you don't need to give a formal argument or any formal proof or anything, right? If you can
But wait, let's hold on. You said if you can give an example of where it fails, you don't need to give a proof. The example of where it fails is a proof, and it fails.
No, I think there's questions is like
Either give an example where it fails or show that it's correct.
yeah,
So both can't happen. If you're given one, you obviously can't give the other.
right,
So you can only give one.
okay,
So if you've given me an example where it fails,
yes,
and it in fact is a correct example where it fails, then you're done.
okay.
But what is the proof that something fails? So what is the proof that a greedy strategy fails? What constitutes a proof that a greedy strategy will fail?
Proof would be you kind of write down the principles or what the policies are.
No, even simpler.
Counter.
Yeah.
It's an example input for which the greedy algorithm chooses the wrong thing and you can show what the right thing was.
How would you show the right thing was?
The optimal would be
How would you show that? So you're trying to do too much work here. You can do less work and still do what I want.
You have the you have to show optimal one, just show the better one.
All you have to do is give an example, run the greedy algorithm, oh, the answer is 5, stare at it for a while and say, oh, look, here's another answer. Value is 6. Greedy fails, done. Is 6 optimal? I don't care. Maybe the correct answer is 10, who cares? Greedy has failed. We're done. So you're doing too much work. Don't do that much work. All you have to do to show that the greedy algorithm fails is provide an example, run the greedy algorithm as stated, get its answer, stare at it for a while, get divine inspiration, drink some coffee, get another example. Get another solution, sorry, for the same example, right? That is better. Which you can sort of prove that is a better solution by inspection. Right? If you're trying to find a bunch of intervals that don't overlap, well, give me a bunch of intervals that don't overlap. That's it. So providing context is very easy. Right? And you've done this in class. You've proposed greedy strategy in class, and you've all come up with examples where it doesn't work. So that's exactly what you have to do, and that's all you have to do. Now, if you prove it correct, then again, we have looked at two templates for proving that a greedy algorithm is correct. The kind of the race template, where you keep, at every step you make sure you're doing better than opt, or the morphing template, where you sort of say, look, I have one solution, opt is one solution, I can change one to the other without changing cost. One of these two templates will need to kick in order to argue for optimality. So again, when you're thinking about how to prove it optimal, don't try to think about these two templates. One of these two templates is going to apply, at least the problem. Okay. Good, very good.
Where do you put comments on the Reddit homework?
So, okay, so in Canvas, when you look at your grade, right, you see where so all of you should have received comments on your grade.
Right.
In that field, there's a little text box below, and you can type in a response. And once you do that, it'll be triggered, an email will get triggered to us.
Okay.
Saying, okay, someone has posted a comment there, and we'll automatically know there's something going on. Right? And again, it's easiest to do there because it's all in one place. You get the whole history of the discussion, and it's there for the entirety of the class, and you can go back, a month later and say, okay, what is the discussion on this and what happened? And so it's all in the log. It's not lying in your email somewhere. You can't find it. Did you find it? On your phone, it'd be hard to see, but if you can, yeah. On the, anything else? Yes.
So, when you have problems where you need to find an algorithm and it needs to meet a certain performance, it feels like there's two ways at least that comes to mind in trying to solve that. One is finding a formula that already fits that performance and then converting it so it solves that problem.
So you mean like, I want an n log n, oh, it must be divide and conquer. Let me try to use divide and conquer and see if I can do it. Is that
Right, so there's that way,
Yeah.
or you could just try to come up with an algorithm and then figure out what the performance is and then optimize it. I'm
Right.
wondering, what would be your recommendations in trying to find an algorithm for a problem?
If I'm asking for n log n, it is highly unlikely that you're going to do anything except dividing. It can happen, but it's unlikely, at least in this class. So you might as well start with the template.
Okay.
If I'm saying, oh, show me an algorithm that runs an n squared k squared time, right? Not that maybe there's an example of this kind somewhere. There's a good chance that it's a dynamic program. So you could apply with that, but my certainty is less. One of the advantages of the second approach, of not worrying about the runtime, of just trying to come up with anything that works correctly, is that it helps you build intuition for what's going on in the problem. So even if your initial solution is crappy and runs in n-cube time, you have learned something by doing it. And now you can actually say, oh well, this step seems wasteful. Let me go optimize it. I mean, when you all write code, hopefully you write your code to be correct first, then you sort of optimize things. You do profiling, you sort of check and see where steps are taking long. The same thing works here. You write something, it works. It's horribly inefficient, but it works. And now you can try to optimize it and see, okay. I mean, in some sense, the very design of dynamic programming comes from, oh, I have this recursion. Oh my God, it's taking exponential time. What the heck is going on? Oh wait, I could have optimized these operations and look at it. So I don't think there's any one rule. I think both, I like the way you've outlined these two approaches. That's exactly how we always do it. With one of the two and sometimes both at the same time, just kind of think about it. Which one works better depends. But that's like I said, for n log n type things, more or less you're using divide and conquer. For things else, you might want to try different things and see, and then try to optimize afterwards. Okay? Other thoughts? Gary?
So, for divide and conquer algorithm, can I make a statement that any divide and conquer algorithm, its recurrence form will always be of the form of master theorem, always be one of the cases of? Because I read about like the linear recurrences and other kind of recurrences, it just seems, I mean, like
This is not true.
That's not true, okay.
Yeah. For example, quicksort. Pick a random element. Use that to split the array into things above it and things below it. Recurs on each side. Okay. Okay. What's your recurrence for quicksort? P of n is equal to, so I have my array, I pick a random element, and I have things below it and things above it. So I know I have n1 and n2. Now what do I do? All I know is that in expectation, I expect that n1 and n2 are roughly at least n over 3. We don't know this, but we can sort of show this. Then you can apply the Monster theorem in expectation. But what you have here is really what's called a probabilistic recurrence solution. So just because you're doing divide and conquer doesn't mean you're going to get a clean application of Monster. It might take some work to get to it. Now, will you eventually get to something that sort of looks Monster theorem-ish? Probably. Yes. So in a sense, I agree with you. In another sense, I don't.
And it's because you're making it a pivot.
Randomly.
That's
Yeah.
why.
And when we talk about randomized algorithms, we'll see how analyzing these can get a lot trickier. Because now you have a random variable which is controlling the split. So any given split is not going to be nice, half and half. It's going to be different, but on average it looks like half. So how does that change the recurrence? Well, it should change it too much, but it does change it a little bit, and you have to analyze this differently. So yes and no. So yeah, Monster theorem is a good handle there, but it doesn't always work. And even the median finding, right? Even simpler. If you look at the median finding algorithm, the recurrence looks something like this: T of n is equal to what is it? T of n over 2 plus, I'm making this up now, but it's something like this. Not a Monster theorem recurrence. Sort of a divide and conquer. Is it divide and conquer? It's really more like a decimation, but that's okay. It's sort of like, but now you can't apply it to Monster theorem. There's a much more powerful hammer than the Monster theorem. It's called the Akra-Bazzi theorem, which allows you to handle things like this as well. And even if you have weird sort of floors and ceilings and all, you can do all that stuff. And that's what you could apply then in those cases. But even that doesn't cover all cases. Right? With things like Fibonacci's and all, you need this annihilator method that I mentioned, that I linked to in the notes, which is even more complicated. So, depends. It's a good tool, but it's not a perfect. It doesn't work 100%. But again, a lot of these things are about building intuition. It's okay to sort of squint at this, pretend to apply the Monster theorem, get a guess for an answer, and then see what it works. That's okay. Because plugging an answer in and applying induction is an actual proof. So use the intuition, get a guess, check it with an actual proof.
Are you going to post the solution to
Yes.
online?
Yes. That's right. Yeah. So basically, we're going to post a version in the templated form that we would hope to see your answers in. Okay, let's continue. So last time we finished, just in the last second, we were talking about this modification of flow, right? We were saying, suppose we change the constraints in our flow problem, and along with, capacity, we don't want to burst the pipes. We have a demand, we don't want sludge to accumulate in the pipes as the oil is going through. So you want a minimum flow in each pipe. And we said that there's a way to transform our problem into one where we can apply a regular flow, right? So the argument was something like this. Suppose you have an edge, you have a capacity, but you also have some kind of demand. And the goal is that you want for each edge right? So you have a minimum flow at every edge. The solution with like Ford-Fulkerson is not going to give you a guaranteed feasible solution. In fact, there may be no feasible solution here at all. Right? And we drew an example last time where there's no feasible solution. So the question here is not so much what's the flow, is there any flow at all? And so the question of is there a feasible flow at all, we said can be reduced to the problem of just solving the max flow. And the way we said it was, let's create the super source and connect it to this endpoint and a super sink. And what we said was that we're going to put a modified capacity here, right? And you're going to put a capacity here of dE, and you're going to put a capacity here. Okay? And you can do this for every single vertex. So then if you have multiple, what will happen is that you'll have multiple edges from the source to a particular vertex, you just combine them into one gigantic flow. Okay, because there's an edge from S prime to U for every edge coming out of U. So there'll be multiple edges from S prime to U, just combine them into one big edge. And the claim was that the claim was that a feasible flow in the original graph will give you a saturating flow in G prime. And by saturating flow, I mean so there's no leftover capacity, they're full. And so if this claim is true, that we have a solution to our problem. We take our problem, we transform it to this new graph, we run max flow in this new graph, look at the max flow we get, check if all the edges coming out of the source are full. Because obviously that's the max flow you can possibly get. If they're full, say, yep, there's a feasible flow. If they're not, say, no, there's no feasible flow. So the question is, can we prove this statement? Right, so once again, we're taking a problem, we're reducing it to a flow problem, and now we have to prove that in fact the answer we get is correct. So this is this. So this was in some sense step one, which was do the reduction. So step two would be that a feasible flow implies a saturation flow. Can we prove that? So can you prove that a feasible flow in the original graph can give us a saturating flow in this new modified graph? How would we do that? What do you think?
Are there two cases that make it infeasible? One is that demand isn't met, and two is that it exceeds some capacity?
Yes, except that we've started off by assuming we have feasible flow. So what we want to, the way to show that this would fail would be to say that the feasible flow does not give us a saturating flow here. Or conversely, when it proves, say, take any feasible flow here that satisfies all the unusual constraints that we have, and find a new flow here that is saturated. So the proof of the statement would be to take F here, which satisfies all the constraints of demands and capacities, and change it to get some F prime that is now saturating in this modified graph. So how would you compute this F prime? So in other words, for any edge in the original graph, there's an edge in the new graph. What should be the flow that we want on the new graph?
Has to be maximum.
Sorry?
The flow has to be maximum.
We don't know that yet. We're just saying, let's construct the flow, then we can check if it's maximum or not. But you're right, it has to be maximum. So we know that, we would like to show is that you can do this with flow that saturates all the edges coming out of the source. Right? So in particular, if you look at any edge, UV, right, it has some flow in the original graph. And since it's feasible, we know that DE is less than equal to F, which is less than equal to CE. Okay? So let's define F prime of E is equal to F of E minus D of I. Because we know that the flow is feasible, we know that this flow is greater than or equal to 0. Right? By the fact that this flow is feasible. Okay, so let's put this But say this is the flow we're going to put on this edge in the new graph. Okay? So what should the flow be now on any edge from S to V? That's a new edge. We have to somehow say what the flow is going to be on that. Well, we want to saturate, right? So it's going to be basically the flow on this is going to be the sum of all the demands of the edges S to V, right, for all V. Similarly, the flow on V to T is going to be the sum over all V. Oh, sorry, we've got a mistake here, right? So, sorry. This will be what?
UV to U.
UV or VU? So the way I've written it would not be VU, it would be VU, not UV.
Yeah, that's what I think. Because
But I think I may have made a mistake earlier. So let me correct this actually. So this, this is what I was wondering. There was something I thought was wrong. Good. Okay, now I feel, I had made a mistake earlier. It had been bothering me for a while. There was something wrong, and now I realize what I did wrong. Here's what I did wrong. This is not correct. What I want to do here. What I want to do instead is this. This makes more sense. Why? Think of it this way, right? What I want is a certain amount of flow on this edge. I'm splitting up into the non-limited flow on this edge and the extra flow that's coming from here to supply the minimum. This actually makes more sense because now what's coming out is the same CE in some sense as what was there before. What I did before made no sense. So, and in that case, this also.
Can you add arrows also from U to V or?
Oh, no. Yeah, there was
The
an error.
direction from U to V, V to V.
That was always there, right? The original graph was still directed.
Okay.
So that is not changing. And then similarly, the other mistake I made is yeah. This is going to be yeah, done the wrong way. So okay, so we have something, I changed something, now it's something else. Let's see if this actually works. Okay? That's the only test that's going to work. Let's try to prove it. So, now what I'm going to say is that I have my flow on the edge, I keep this. This is the same as before. This I'm going to be is basically this. So now, the total flow going from S to V is the sum of all the flows of things going in, which is now consistent with what I said before, because this is the end point. And similarly for this, I'm going to say this is all the and remember that in my previous example, I also had one super edge going back from S to T. So it measures a huge pipe going back. Okay? All right. Now, we've now set, so now I set the flow on T to S to be equal to the total value of the original flow.
Can I ask a question about your graph, the one that you were just modifying? In the reading, I'm not sure if I understand this correctly or anything, but isn't S and T still supposed to be there? on the graph.
It's an S prime and a T prime. These are S prime and T prime. There's a new source and
Right, but I mean like, so you add an S prime
Mhm.
before, but isn't S still part of the graph?
Yes, there is still an S in the graph.
Okay.
Because in some sense, I've just created a loop here. I'm not adding new flow. The new flow is still being generated by the original graph.
Right.
Yeah.
So is there no demand between U and V or? I'm trying to-
There is. The original demand, the specified demand was between U and V, a value D. In my new graph, I have no demands between U and V. I modified the graph to a regular max flow graph, where there are no demands on any edge. Right, that's my goal. My goal is to convert a graph where I do have demands on edges to a graph where I don't have demands on edges. Because once I don't, I can run regular max flow. But this weird demand thing was causing me trouble. So I wanted to get rid of it. Okay, so now we have this construction and we have a claimed assignment of modified flows. So the question is this a feasible flow? And is it saturating? Yes. Here,
So second one.
second one, this is W.
What is U?
No, F dash.
Sorry, here?
Yeah.
No, V. It's still V, any vertex V. I mean, I could call it U also. I mean, this is just for any vertex V, the modified flow from V to T prime is the sum of all the demands here. I mean, that's a statement. I had to justify it, but that's what I'm saying. Okay? Yes? Okay. Is this a feasible flow in the modified graph? First of all. And then is it saturating? Well, first of all, if it's feasible, it is saturating. Why? Because of this. If I can actually do this, then clearly this flow is saturating all the edges coming out of the new source, right? This new S prime. Because that's the total capacity we've given it. Right? Remember the total capacity? We basically said there's one edge of dE. Well, if you add them all up, that's the total flow. That's the total capacity. So if we are actually able to show that this flow is feasible, it is saturating. Yes?
So you modify the graph.
Yeah.
V becomes sink.
You're basically saying I'm adding a new source and sink, and I want to look at the flow from this new source to this new sink.
But in your graph, everything goes to V, nothing comes out of V. So V is the same.
Everything goes to V. I don't know what that means. What does that mean?
If you go back, yeah, nothing comes out of V.
No, but this is a particular edge. V is now going to connect to other edges.
Oh,
This whole construction is for a single edge.
part of the graph.
Yeah, so this whole thing I'm doing is from one edge.
So do you create different S prime and T prime
No,
for
same,
every edge?
no, same S prime, T
Same
prime.
S prime, T
So
prime
for
all
example, I
edges.
see this gets messy, right? But let me draw it with a different color. So now let's see that, okay? This is another edge in my graph. So now I have,
This is partial of the.
yeah, so I drew it one edge at a time. I didn't want to draw the whole thing. But you do this for every single edge. So that's why now, if I had multiple edges coming in, let me draw a third one since we're in color mode today. So if I have another one, let's say X, right? Then there will be another, oh my God, this is terrible. Here. You get multicolored spaghetti. But that's the idea. I should have been more clear about this, but you do this for every single edge, not just for one special UV edge. So you get this mess of stuff. Okay. So, like I said, we have now said, given the original feasible flow, I am going to construct what I claim is a valid flow in the new graph. And this is the way in which I'm constructing it. So I've specified the flow values for every single edge, the original edges, and all these new edges I've added in. If in fact this flow is a valid flow, a feasible flow, then this here guarantees that my flow is saturated, because this in fact is the total capacity of everything. Because the total capacity of flow coming out of the total capacity coming out of the new source is the sum of all the demands, because of what we saw earlier. If you added the blue and the red, I added the white and the red, those are the two different demands coming in. So all we have to show now is that this flow is in fact feasible. So how do we show this flow is feasible? Well, we have to show that it doesn't violate capacity constraints, right? And that all flow conservation happens. So first of all, capacity constraints. Let's look at this new flow on this edge. So first of all, it's more than 0, which is good. Does it violate the capacity constraints? Yes or no? If yes, why? If no, why? Again, thinking rigorously here. Why does this flow not violate the capacity constraints? Or why does it satisfy the capacity constraints? Well, F prime E is equal to Fe minus dE. F was feasible, so F is less than CE. Since Fe is less than CE, F prime E is less than or equal to CE minus dE. But that's the modified capacity. So let's say this correctly. So we have the flow F prime. We have the flow F prime E, which is equal to F of E minus dE, which is less than or equal to CE minus dE. Because F is feasible. But this is less than or equal to C prime E. Because we've set C prime E to be exactly CE minus dE. Therefore, F prime E satisfies capacity constraints. But what about the other edge? Yes?
What is the demand is negative? Can it be negative?
In this formulation of the problem, we have specified that the demand, if the demand is negative, that's like saying the demand should be at least minus 5. Since in any flow problem, the flow is always at least 0, this is trivially equal to the actual flow problem.
Like I'm thinking incorporating the opposite direction. Like
It's even simpler. If the demand is negative, it's saying the flow should be at least minus something, then that means that as long as I can make sure my flow is at least 0, I'm happy. But in the regular max flow situation, the flow is always at least 0. So this is a trivial reduction of max flow. The only cases where you have problems with the flow is when the demand is positive. Right? So this is a formal statement. Okay? Alright. So if prime E satisfies capacity constraints, what about the other edges? So we have other kinds of edges, right? So we only count, what about these kinds of edges? Well, this by definition satisfies the capacity constraint because this is the capacity. This by definition satisfies capacity constraints because this is the capacity. The capacity of this edge was infinity, so therefore this satisfies the capacity. So capacity constraints are good. It's all fine. The next question is the conservation constraints. Right? So that's a little bit trickier. So how would you argue about the conservation constraints? So this, you basically have to argue that for every new edge, every edge here, whatever flow is coming in is equal to the flow coming out. That's what the conservation constraint is. Right? And this is tedious algebra. I'm quoting directly from the notes. So let's think about this. Before we try to write it down, let's think about why this should be true. Or should not be. What do you think? So again, we're looking at the modified flow. We want to show that it satisfies the conservation constraints. You don't manufacture flow in the process, given the assignments we have. And to keep things simple, let's assume that let's just say we have one edge and we have something coming in and something coming out. How do we know this is going to satisfy capacity? So conservation constraints. What do we do? So we have some flow on this edge. We know it's some flow F prime. And we have some other flow F prime here and F prime here, right? Will these all, ideally they should all be the same value. But we know that, let's draw an actual example here. So I'm not doing a proof yet, I'm just building intuition, right? So I'm saying, okay, I have these three edges. Okay, this is going to be FE1 minus DE1. This is going to be FE2 minus DE2. And this is going to be FE3 minus DE3. Right? Now, of course, in the original graph, there was no D, there was just the F. And the F had to be same if there were just these three edges and nothing else. So the F is the same for both, all three of them. It's the D's that are different. And that's bad, because now I have different numbers here for different D's. So this seems like this would not satisfy conservation constraints. Except, what's going on? What else is happening here?
You're supplying a D.
I'm supplying a D here.
No.
I'm supplying a DE1 here from the source, the new source. I'm supplying a DE2 here from this source. I'm supplying a DE3 here from this source. Right? That's the way we constructed this new graph. So what's going to happen is the flow coming out at this point is going to be F. That's going in. And what's going out, remember what's going out is DE2, right? So if you look at this node here, we have FE1 minus DE1 coming in. We have DE1 coming in. We have DE2 going out. And we have FE2 minus DE2 going out. Remember that FE1 is equal to FE2 because in the original graph there was just this chain of edges and the flow had to be the same. Is this satisfying conservation constraints? Yes, because this plus this is FE1. This plus this is FE2, but FE1 was equal to FE2. So at this vertex, it's actually satisfying the conservation constraints. So this gives us, this is not a proof, but this gives us some intuition as to what these weird things are doing. They're basically supplying that phantom flow that was there in the original graph, which we've removed in this graph. In this graph, we've subtracted out that minimum required flow, but we have to sort of put it back in. So we put it back in here at the end, magically. And so this gives you the idea for how to actually write the proof. You basically look at every vertex, right? And you sum up all the flow coming in, which is going to be, from one edge it'll be this, another edge will be that. But for each of those edges, there's going to be a corresponding D coming in from the source, because that's exactly how we construct it. So all of those things cancel, and what you get going into the vertex is in fact the net flow you had in the original graph. Okay? Now in the original graph, the same net flow is going out because it's feasible, but that gets split up in this other way. And therefore, at every vertex, you now have conservation constraints in your graph. So the flow is feasible because it satisfies capacity constraints and conservation constraints. It is saturating because, well, it saturated. Therefore, we have now proved that the feasible flow gives us a saturated flow. We are 2/3 of the way to a proof of this. Because the last part is and here, what we need to do is start off the other way around. Assume you have a saturating flow F prime in the modified graph. Use it to construct an actual flow in the original. And now you should see how that's going to work, right? If you have any particular edge with some F prime on it, what do you think is the actual flow you want to put on this edge? Well, the actual flow you want to put on this edge is going to be F E is equal to F prime E plus A. And similarly for the other edges. And then now you go and prove that this is in fact a feasible flow, satisfies all the capacity constraints, satisfies the convolution constraints, and it will more or less be for the exact same reason. Okay. Again, the proof how we do it is in the notes, so please read that. And then you have finally shown that in fact feasible flow on the original graph is equivalent to saturating flow on this graph. We have now solved the problem of dealing with edge demands. Okay, so edge demands. Which means that if we have a problem where we sort of need edge demands to make sure the problem can be captured correctly, we don't have to worry because we know we can capture it in a max flow. Here's a quick exercise for you. Suppose I had a different kind of constraint. Suppose I said that my nodes, think of them as junction points of my pipes, are not very big. Each node has a capacity. So the amount of flow going in, and of course the same flow going out, then the flow into V is less than equal to some capacity of V. And I give you these capacities at a time.
Can you just make
Sorry?
that one node into two nodes and have an edge with that?
Oh, so you're jumping. So we now have a proposal for how to capture this in a max flow setting, and the proposal is to take such a vertex, which has a capacity attached to it, and replace it by two nodes. Let's call this U and U prime. And now do what?
Make that edge have that lowest.
What is the direction of the edge?
From U to U.
And what do I put the capacity of the edge?
E1.
The capacity. The capacity of this edge will be C,
Yeah.
right? Okay, what about all the edges coming into U? How do I hook them up?
The original edges to the node coming into the node.
So all the edges coming into U will come into U here. All the edges going out of U will go where? U prime. Okay? So intuitively this makes sense, right? You're saying I'm going to put a choke on this vertex. The only way now to put chokes on things is through edges, so I'm going to create this extra edge. But of course now, this is the first part. You've got the reduction. Now you have to prove it. Prove that a feasible flow on the original graph will give you a feasible flow here, and that a feasible flow on this graph will give you a feasible flow on the original graph. Once you have that, then you can say that a max flow on the original graph is a max flow here, because it's the same flows, same values. So in other words, you want to show that a flow of F in the original graph is a flow of F here, and a flow of F in the new graph is a flow of F in the original graph. And the max flow there is a max flow here, and you've got the match. So just like this, there are other things. You can now say, well, what about if nodes have demands? Right? Well, now you can say, well, nodes have demands, and I now have a demand on this middle edge. And now that I know how to solve from a previous problem. So you can do all kinds of crazy things with flows and still capture in the flow context. Up to a limit. And that this is how you reason. And again, the reason we want to know about these transformations is because one of the main goals is to take problems and map them into flow problems. And we'd like to know that there's flexibility in our map. We don't have to work too hard to get exact and maximal form. That even if we allow node capacities and demands, it kind of works. Okay. In the time we have left, I want to now take you through one such example of how you take a problem that looks nothing like a flow problem. Okay? And I'm going to do it again step by step so we can see this procedure, which is very important. So understand how this works. Are there any questions so far? So again, if I ask you in the homework, oh, I want to add this constraint to my flow network, can I solve it using max flow? The way you're going to show me that you can or cannot is by saying, okay, here's the reduction, and here's a proof that a flow here gives me a flow there, and a flow there gives me a flow here. I get a reduction. So 3 things. All right. Let's take an example. And we're going to take a very primitive example. It again might not capture the state of the art on how to solve this problem, but it's a good illustration, and in fact for a while was the way people would think of this problem. And the problem here is what is called foreground background detection. So if you're an autonomous car driving in the DARPA Grand Challenge in the desert somewhere in Arizona or Nevada, I forgot where they had it. What you'd like to know is, okay, where's the road and where's the sky? Kind of basic thing that's useful to know if you're driving by yourself. And of course, if you're in the desert, it's not that hard. It's not that easy to tell where the ground ends and the sky begins, especially if it's a polluted day or something. So this is just a story to motivate why. In fact, in the original DARPA Grand Challenge, the first one, a lot of the robot cars were having trouble just distinguishing road from sky, and they would go off course because of that. Now, of course, they're more sophisticated. At that time, that was a hard thing to do. So this problem of detecting foreground from background is a basic problem, and very basic elementary problem in computer vision. And so formally, you can think about this is that I have an image, which of course is a collection of pixels. And I want to figure out which pixels correspond to foreground and which pixels correspond to background. And then after that, I might do some further processing. It's a very, very simple point problem. So the problem here, so I want to say, okay, this is foreground. I want to label all the images, all the pixels like this. Okay, this is my goal. So given an image, which is a set of pixels, label each pixel as either foreground or background. Now, of course, without any other knowledge, you can't do anything. So what happens is you often put various filters. You say, okay, look, I have some other filters that give me some belief. Maybe I built a probabilistic model. Maybe I have some prior knowledge about the underlying domain that give me some belief about the foregroundness or the backgroundness of the pixel. Okay? So let's say for each pixel, let's call it I have two numbers. I have an AI number and I have a BI number. This is some belief number. Think of it as a problem, think of it whatever you want. Think of it as a strength of belief. The larger it is, the more you believe strongly that this is a foreground and this is background. And the reason to have two numbers instead of just one and one minus that or something is that you might have different processes for deciding whether something's background. You might have natural ambiguity. You might believe very strongly that something is both foreground and background. You want to allow for those things because you don't know really what your system is doing. So if you have these numbers, and if this is all you had, this would be a very easy problem. For each pixel, check which number is bigger and declare that to be the answer. But of course we know that foregrounds and backgrounds are not just arbitrary pixels, there's some kind of spatial coherence around them. In other words, what I don't want is to have an image which gets labeled like this. I mean, it could happen, but it's highly unlikely. If I actually hold up a checkerboard pattern and with holes in it, maybe I will see this, but generally speaking, I don't expect this to happen. Okay? So we have some sense of pixels that are nearby to each other are more likely than not to have the same label. Right? Two foreground pixels will be together, and of course there will be edge cases where you will actually transition the boundary, but there should be fewer of those. So we might have some more information of the form, some PIJ, that is the belief that I and J are similarly labeled. Right? So if I strongly believe that two pixels should be similarly labeled, I put that number to be very high. Right? If I strongly believe that they're not similar, I put the number to be very low. So this is the input to my problem. I give you an image, and I give you AIs, BIs, and PIJs. And I say, segment this image into foreground and background. This has nothing to do, at least on the surface, with the flow problem. And yet, you can solve it using a flow problem. So what I want to do is kind of walk you through how this might work. So, what are the things you need for a flow formulation? You want a graph, right? Do we have a graph here? Huh?
Yeah, we could make a graph.
How do you make a graph?
have a node, like each pixel be a node,
Yeah.
and then have its edges be directly connected to the pixels around it.
What's around it?
I guess if it's the corner, it'll be the right.
Right,
bottom.
but think about what this is saying. Maybe you just want to connect everything up to everything. And just put this as a kind of a weight on that edge. That's one thing you could do.
Right.
Possibly. I don't know yet. So we have some graph. So we can get a graph. For example. Okay, but we also need directed edges. We don't have any directions here. We also need capacities. We don't have any capacities here. We also need a source and sink. We don't have that either. And when you solve a flow problem, you get flow, right? You get a sort of set of flows on edges. But what do we want here? We want a set of things. We want like a foreground and background, right? So we don't have flow either. So in our attempt to convert this to a flow problem, we're not doing very well. We don't have any of the things we need to make this look like a flow problem.
Well, there's one binary. It's either foreground or it's background.
Okay.
And in the formulation of a flow problem, there's one binary that's the source and the sink. Maybe there's a.
But the source and sink are not binaries, they're just there, right? There is a binary thing involving choices of vertices in the flow problem somewhere.
Direction.
No. That's the choice of an edge. Not the choice of vertices. Where do we choose vertices at all in a flow problem? Maybe not directly, but indirectly. Remember, flows are a Jekyll and a Hyde. There's the evil twin. Who's the evil twin of the flow? Sorry? No. There's the mirror image. There's the flow and there's the... Who said that? Who said cut? The cut. There's a flow and there's a cut. There's a cut and there's a flow. They're kind of duo. They sort of play these games with each other. Where you have a flow, you have a cut. Where you have a cut, you have a flow. Cuts are what? They're sets of vertices. Right? You're picking some vertices, aren't you? So maybe this is not a flow problem, but it's a cut problem. But that's okay because they're kind of dual. So maybe we need a cut. Okay, so we've done a little bit of thinking here. We've got something. We're not quite sure where we're going with this yet. Let's go back to our problem and say, well, what is it we want to do? What is our goal there? Can we come up with some kind of cost function we want to optimize? Because that's what we're doing in flow, right? We're optimizing something. So let's go back to our formulation and say, okay, we have these foreground pixels, background pixels, and belief. How would we evaluate the quality of a solution we produced? What do you think we might want to do? Something very simple. What would we like to see? Well, if we named a pixel as foreground, we'd like to get the benefit of calling it foreground, where the benefit is expressed in terms of its belief. If we call a pixel background, we'd like to get the benefit of calling it background, right? So we might say something like the quality of a solution is this. So let's say that a solution to our problem is a set of foreground pixels, and of course the complement will be background pixels. Okay. So now we say the quality of the solution f comma b is equal to the sum over all I in f ai plus the sum over all I in b pi. Right? This is the profit we're getting from using our beliefs to decide what to do. But we also have this Pij, we have this sort of spatial coherence constraint. So we want to say something like, well, I want to punish you if two things that were supposed to be together are being put separately. So in other words, subtract out sum for all I comma j such that ij intersection f is equal to 1. So exactly one of I and j is an f. So the edge is going across it. This is just a shorthand way of saying either I is an f or j an f, but not both. Right? So we're subtracting because these were pixels that were meant to be together. I know that I think so. They were meant to be together and we separated them out. And so we're paying a penalty for this. So you subtract. Yes?
Are we assuming, somehow assuming that a pixel can't be a foreground and background?
Yes.
Pixel,
Because our goal is to partition
Okay,
the pixels into foreground and background. This may be a modeling choice that is wrong.
right. In real life, pixel, it can't easily be both, but.
Well, I don't know about real life. I'm saying this is one modeling choice that could be wrong. And you might change that modeling choice, in which case you get a different problem. And we could go and solve that problem too. Right now I'm making this particular modeling choice, say I just want to have a clean separation of foreground and background.
So in a flow problem, like if we're modeling just something kind of random, if the outcome is not binary, does flow kind of fall apart then?
Output, what do you mean by output? There's no binary output. I'm outputting
Well,
a set.
the pixel's either foreground or background, so.
But I'm
it's-
outputting a set.
Right,
Right, that's my output. Because my output is a set, I'm thinking, okay, maybe a cut is what I want. My output might be something else, in which case a flow might be what I want. This depends on the problem. So I don't think your lens of binary or not is a helpful
well,
lens.
so if a pixel can be both foreground and background,
This formulation is wrong,
okay,
but this has nothing to do with flows.
okay.
This cost function is wrong. Because I'm only paying, I'm assuming everything is in one or the other, that these two sets don't intersect.
Right.
I think actually technically in this particular case it won't make a difference.
So,
I suspect it won't make a difference here. You just have duplicate things, that would actually be fine, but I can check that. Yeah,
let me ask you this, let's say if your pixel could have one more value, green, could you still apply this formulation?
what is green?
I'm just making up, let's say you have foreground, background, and some more, and the third dimension also.
Middle ground. Say, for example. That's what
Second.
you want a third parameter.
Yes,
Yeah, okay.
could you still apply this kind of formulation in the next flow and this?
Well, I haven't applied max flow yet. I'm just modeling the problem. There's no flow here. Right? We could be taking a class in computer vision, I could be doing this slide here. There's no flow yet. I'm just modeling it somehow. And this is a more general comment about modeling problems, right? And one of the reasons a lot of you, when you're going out to do your jobs or sort of think about algorithms in a sort of a live context, you're going to be taking some fuzzy problem and trying to model it in a way that you can apply reasoning to it to make it more precise. Gaps in your model will mean that your solution will have certain limited predictive value. And that's a valid discussion you have to have. But we're not having a discussion right now. We're not solving the computer vision. We're saying, let's just take a model of the problem and see how you can map it. You might have a different model problem. You might still be able to map it before. I don't know. But we're not there yet. We're still doing this one. Okay. So I have this cost function, and hopefully we agree that if this number is big, our answer is better in terms of our input. Because it's optimizing the things we care about. So our goal is to find f to maximize q. B is implied, but it's complement to f. But now we have a problem. Because in cuts, what are we doing? We're minimizing cuts. We're not maximizing cut values. We're minimizing cut values. In fact, as we will see shortly, maximizing a cut value is a very hard problem. So this seems like it will be bad for us because we want to map it to flows, and flows said we want to minimize cut values. Yes?
Well, when you're given a probability, 1 minus probability is, maximizing the probability is minimizing 1 minus it.
Very good. So can we convert this into a minimization? So let's see if we can do that. Can we, instead of maximizing something, can we minimize something else? Like instead of maximizing happiness, can we minimize sadness? Is one way to say this. So what would be a version of this? Well, here's a simple trick that often works. So let S equal to sum of AI plus BI for all pixels. So that's F union B. You just add up everything. Clearly this is a constant, right? This is just part of the input, just adding up all the numbers. And now let's compute okay? If you do the algebra now, what you will get is this. It's going to be equal to the opposite. Minus the probabilities of the before. That doesn't change. So here now we're saying, instead of maximizing our happiness or alignment with our belief, let's minimize our disagreement with our belief. These are pixels that we put in the background. We're losing all their foreground mojo. These are pixels we put in the foreground. We're losing their background mojo, and we're unhappy about it. And again, we're unhappy about this as well. So now clearly, maximizing QF is the same problem as minimizing CLF. Because S is a constant. This goes back to exactly what you just said. So now we have something where we want to find a set and we want to minimize something associated with that set. So now we're feeling a little bit happier about this. Right, so we want to minimize some set, something of a set. But what do when we do min cuts, what is the thing we're minimizing of that cut? We're minimizing the capacity of that cut. Right? The min capacity cut is the gives you the max flow. So somehow this means we want to somehow express this quantity here as the capacity of this cut in some way. And this is where we can now start thinking about how to apply a flow formulation, or rather a cut formulation. So look at these carefully, right? Here's what we're going to do. Imagine our graph. We'll create some source and sink. We have all the vertices in our graph, the pixels of our image as vertices in this graph, and we're going to find some cut. Right? This is the foreground, and then this is the background. Right? So let's look at any particular vertex that we declare to be in the foreground. Let's go back to this column. What is the contribution to the cost of that pixel? Right? Well, if that pixel is in the foreground, you're paying a BI cost for it, right? As well as all the edges out to things that are not in that set. Okay? So to pay a BI cost for this pixel in the foreground, it must be corresponding to some edge coming out of that vertex. Yes?
Is that minus sign right?
Yes.
This is the penalty we're paying?
Yes. Oh. Oh. No, you are in fact correct. That's a penalty of it. And because you're right. Thank you. Very good. Yeah, we don't want minus signs in our cut formulation. Good, thank you. So we're paying a contribution for this, and we're paying a contribution for all of these things. Okay, but let's look at that vertex. What are the edges that would contribute to the capacity of the cut for this vertex? Well, it's all edges coming out of the vertex, going either to other things or to the sink. These are the edges from this vertex that contribute to the capacity of this cut. So here's what I'm going to do. Look at this BI. I'm going to label this edge from vertex I to the sink with BI. And for every other edge, I'm going to label it with a PIG. Okay, I haven't put directions yet, I'm labeling it with PIG. Similarly, for every vertex in the background, its contribution is an AI. And so once again, I will have an edge from this, which looks like an AI. and again you'll have other edges coming. So this is the intuition. What this means is that the construction we do is, so step 1, Vi for each I, ij edge for all ij such that Pij is greater than 0. Okay? And we will put edges in both directions. Okay? Because we don't know which way it's going to be, which side it's going to be. Number 3, edge S to I with capacity, let's go back, S to I with capacity AI, I to T with capacity, did I get it wrong? I guess it's wrong. No, okay. Capacity BI. Okay? So I'm building up my reduction now. And now I have a fully specified graph on which I can run min-cut. I have source, I have sink, I have directed edges, I have capacities. And I can run Ford Fulkerson and find a min-cut. By construction, the cost of this cut is equal to this. Right? That's the cost of the cut. And so by minimizing the cost of this cut, I actually have found the solution to the erosion problem. And of course I have to prove it. The proof at this point should be clear that if I get a solution here, it corresponds to a foreground background partitioning of the exact same value. A foreground background partitioning of a certain value gives me a cut of the exact same value here. And so the min cut here gives me the partitioning element. We're a bit over time, sorry about that. I just realized we're over time. We will continue this discussion on Tuesday.